Hi viewers, welcome to LMS Solution. Today we are going to see about grid connected solar PV system with the battery energy storage. So in MATLAB, so this is a simulation model of that grid connected solar PV system with battery energy storage. So this system consists of PV array. Okay, so this is a PV array, and then it have battery energy storage, and then it have grid. Okay, so grid we are consider here is single phase grid. So that PV system, battery storage, and then the single phase grid will be connected to the common DC bus. So this is a common DC bus. Okay. So this common DC bus going to be maintained around 400 volt. So we are going to maintain that DC bus to 400 volt. So once you maintain that 400 volt, right? So what will be happen? The power flow happen between PV to battery and PV to grid, and also the power flow happen between battery to grid as well as battery to DC bus. Okay, so we must maintain that 400 volt the DC bus constant, so then only the power balance will be happen between source and load. Okay, so first I am going to start with the solar PV system. So here we are considering PV panel or PV array. So here is I am clicking that PV array. So here you see that, right? PV array having 8 series connected model and then 1 parallel strings. So that means we are using only 8 panel in series. Single panel power will be 250 watts and open circuit voltage is 37.3 volt, and then short circuit current is 8.66 amps, and voltage at maximum power point is 30.7, and current at maximum power point is 8.15 amps. Okay. So then I'm going to check the PV IV characteristics of the considered PV array with the 25 degrees Celsius and varying irradiation conditions. So here we are consider for varying irradiation condition 1800, 600 and 400. So just I'm going to click this one. So then you will see that graph for that IV and PV characteristics of the particular PV array, consider PV array. So here you see that, right? So this is a peak point for a 1000 watts per meter square, and this is a peak point for a 800 watts per meter square, and then this is a peak point for a 600 watts per meter square, and then this is a peak point for a 400 watts per meter square. So while you can see that, right, when it is 1000 watts per meter square, the power generation, the peak power generation from the PV is around 2000 or 2 kilowatt. For 800 the power generation is around 1.6 kilowatt. For 600 is around 1.2 kilowatt, and then for 400 is around zero point 0.8 kilowatt. Okay, and also you can check the voltage also. So voltage will be slightly vary according with the change in irradiation. Okay, so this is a peak point. So we need to extract this peak power point according with the irradiation and temperature condition. So why it is important, right? If suppose we are going to operate that system in this point, right, then for example the current irradiation will be 1000 watts per meter square at 25 degrees Celsius, but you are operating the system in this point, right? Then power you can extract from the PV around only 1.6 kilowatt alone. Okay, but we are wasting that remaining power, right? We are not utilizing that remaining power effectively. Why I'm telling, right, that peak point is available in this point, right? So it that means for particular irradiation condition the peak power is 2 kilowatt, right? So we need to operate that PV in the particular point. Okay, so for that we need some algorithm or control logic. So that control logic nothing but the maximum power point tracking algorithm. So in this system, right, in this grid connected solar PV battery system, the PV going to be the PV maximum power going to be extracted by means of P&O MPPT algorithm. Okay, so here we are using conventional P&O MPPT algorithm for extracting that peak power from the PV array. It means that P&O MPPT when we used to extract that point exactly. Okay, So that going to be used to for extract the peak point at the different irradiation and temperature condition. Okay, so for that purpose only we are using that P&O MPPT. So how that P&O MPPT going to be work, I am going to explain here. So just I am going to use only one operating point, that means 25 degrees Celsius and 1000 watts per meter square, and I am going to click plot. So here you see that, right? So this is a graph for IV and PV, IV PV and PV IV characteristics. So this is a variation of power with respect to change in voltage. Okay. So when system is short circuited, the voltage will be zero and power also zero. So this is a point, right? So this is a short circuit current 8.66 amps. Short circuit voltage will be zero. Okay. So here we will see that, right? So 8.66 amps, right? And then so this is a open circuit point, so voltage will be 298.4 volt, then current also zero. Okay, here this is a peak point for the particular condition, 1000 watts per meter square. The power will be 2 kilowatt, voltage is 245.6 volt, and then current is around 8.15 amps. So this is a different voltage and current setting for the different conditions, short circuit, open circuit, and peak power point. Okay, so now how we are going to apply that P&O MPPT algorithm here, right? So for that we need to have four condition. Okay, so how we have to derive that condition, I'm going to explain now. For example, I'm going to take 2 points. For example, we can separate this portion into two. So this is left side and then this is right side. Okay, so for left side we have to derive two condition, and the right side we have to derive another two conditions. So totally we need to derive four conditions for implementing that P&O MPPT algorithm. So now I am going to consider 2 points. So this is the first point and this is the second point. Okay, so this first point known as, for example, I am going to consider this voltage is V1 and this is V2, and also I am going to draw another horizontal line. In horizontal line here I am going to mark that point will be P1 and P2. Okay, so now we have to consider, that means that PPT algorithm going to be executed with the two samples. Okay, so two instant. So one instant known as current instant, another instant known as previous instant. So based upon that logic, I'm going to consider the V1 is the current instant, V2 is the previous instant. Then I'm going to find out the difference V1 minus V2 and also P1 minus P2. For example, I'm going to consider that difference of V1 minus V2 is negative. Okay, and P1 minus P2 also negative. So both will be negative, right? Then the current operating point this point, right? But peak point is there in this point, right? We need to move this voltage from this point to this point. So for this condition, okay, that means that the sign of voltage difference and sign of power difference will be negative. Then we need to move that voltage from this point to this point. That means we need to increment the voltage. Okay. Same here I'm going to consider opposite direction. So V2 is current instant, V1 is the previous instant. Then we have to find out the difference V2 minus V1. Then that time it will be positive. Okay. So that time will be positive, and also P2 minus P2. So the difference will be positive. Okay. During this time also we need to move this point towards to peak point. That means here also we need to increment the voltage. Okay. So in left side there are two conditions. So negative and negative. Okay, and then another condition is positive and positive. Okay, so here we need to increment the voltage, here also we need to increment the voltage. Okay, and right side, right? So I'm going to consider these 2 point. So in this 2 point here also we have to take this one is V1 and this one is V2. Okay, and this is P1 and this one is P2. So I'm going to find out the difference. So V1 minus V2, so sign will be positive, and sorry, V1 minus V2 is sign will be negative. Okay, sign is negative, and P1 minus P2 is sign will be positive. So during this condition, right, so we need to move that PV voltage, okay, from this point to this point, right. So here we have to decrement the voltage, okay. So when you take the opposite sign, right, opposite direction, V2 minus V1, so this will be positive, and P2 minus P1, this will be negative. During this condition also we need to move that point towards to this point. So here also we need to decrement the voltage, okay. So here you have another two condition, plus minus, minus plus. So in this time we need to decrement the voltage and decrement the voltage, okay. So when we are going to implement the same concept in the duty cycle concept, right, so we need to take that uh, duty cycle value, right. So when we are going to increment the voltage means we need to decrement the duty cycle, decrement the duty cycle. So here we need to increment the duty cycle. So we have to take opposite direction when you have to implement in the duty cycle concept, okay. When you are going to implement the voltage reference calculation, then you have to take that first this condition. When you have to implement in duty cycle, you have to take this condition, okay. So here we are going to implement that when we implement that when we implemented in the duty cycle concept only. So I'm going to proceed with the duty cycle concept. So this is how that P&O MPPT work for extraction of peak power from the PV array. Okay. So now move on to next part. So now here you see that this is a DC link. Okay, already I told, right, this is a DC link. This PV array going to be connected to the this DC link via this boost converter, okay. So the boost converter used to for link that PV array with the DC link, okay, and also used to extract the peak power from the PV along with P&O MPPT, and also boost the voltage from around 245 volt to 400 volt, okay. So this boost converter going to be controlled by means of P&O MPPT. So here you see that, so this is a P&O MPPT we implemented for that PV array boost converter, okay. So here we are measuring the PV voltage, and here we are measuring the PV current. So that means here we are taking the measurement, okay. And then after taking that measurement of PV, so just you have to take the PV voltage and current. So that will be processed inside the P&O MPPT. The output will be duty cycle. So the duty cycle going to be processed here, okay. That means output of duty cycle from the P&O MPPT going to be processed via PWM generator. So that means we are going to compare that duty cycle with the triangular wave. So here we are going to compare with the triangular wave, then it will be generate the pulse, okay. So this pulse going to be used to control this IGBT of the boost converter, okay. So that means pulse from that P&O MPPT going to be control this boost converter, and also going to be extract the maximum power from the PV array. So next you go inside the P&O MPPT. So here I'm going to go inside. So this is a implementation of P&O MPPT. So in order to implement that P&O MPPT, we have to implement that means you have to fix four parameters. So one is initial duty cycle, maximum duty cycle, minimum duty cycle, and a small change in duty cycle. Small change, that means based upon that four condition, right? Already I told, right, four condition. So based upon that we need to increment the duty cycle or decrement the duty cycle, right? So for that, how much amount of duty cycle we are going to increment or decrement, so that is known as delta t, okay. So next you have to fix that initial parameter like b volt, p volt, and d volt. So this is nothing but the current, that means previous instant voltage, power, and the duty cycle, okay. So initially you have to fix this value, and then you have to calculate the power of the PV cell, PV array, and then you have to calculate difference. That means you have to calculate that the difference between the current instant with the previous, okay, for the voltage as well as power, okay. So next you have to check the condition. So these are four condition already told, right. That means the both sign, right. So both difference of voltage and power sign will be positive or negative, then we need to decrement the duty cycle, otherwise we need to increment the duty cycle. So that logic will be implemented here, right. So here is that we are checking the power sign, right? If it is less than 0, power sign is less than 0 in the sense negative, right? And also you are checking that voltage sign. So here also that sign will be negative, then we need to decrement the duty cycle, otherwise we need to increment the duty cycle. So if suppose this condition is not true, that means the power sign will be different, sign will be positive, again we have to check the voltage different sign. So if it is negative, then we need to increment the duty cycle, otherwise decrement the duty cycle. Okay, so these four condition going to be used in the P&O MPPT for calculating the current duty cycle or optimal duty cycle in order to get the maximum power from the PV array. Okay, so after calculating this duty cycle, next part is most important thing. So whether that calculated duty cycle within that limit of that duty cycle, that means already we fixed the limits for the duty cycle is in between 0.01 to 0.95. We need to check whether the duty cycle is between these two limit. Okay, if it is within two limit, no problem, you have to take that value for further processing. That means it going to be processed by pendulum generator for generating the pulse. But if it is more than D max or less than D minimum, so you have to keep that duty cycle which is equal to previous duty cycle. Okay, no need to consider that calculation from that these four condition. Okay, and then here we are taking that that means we are overriding that current instant to previous instant, and then it will be keep on change every samples. Okay, so this is a P&O MPPT implementation in the system. Okay, so next process we are going with the battery energy storage system. So here we are using battery here. So battery is around 12 into 20 is around 240 volt battery, and then I'm taking 48 Ah. So we can change the rating, we can change the rating according with our requirement. Okay, so here you can fix the initial setup charge. Okay, you can fix 50 or 100 or sorry 50, 100, 90. Okay, so initially I'm fixing 50, later I will explain about the things. Okay, so because we are going to control the system according with the SOC of the battery as well as the power availability of the PV. Okay, so later I will explain the detail clearly. So this is that means battery detail, and battery detail going to be connected to the DC bus. Okay, here we are going to use DC bus. How we are going to connect this battery? Right here we are using bidirectional converter. Okay, so the in this bidirectional converter, so why we are using bidirectional converter? Because we need to charge the battery as well as we need to take the power from the battery. Okay, whenever the PV having excess power, okay, so we need to charge the battery. If suppose PV does not have any excess power or PV not supplying any power, right, during night time, right, so we need to take the power from the battery to supply the load or to send the power to the grid. Okay, so for that purpose we need bidirectional converter. So for that purpose only we are using bidirectional converter here. Okay, so next thing, so we need to control this bidirectional converter. So in order to control this bidirectional converter, we are going to use voltage control method. Why we are going to have voltage control method? Already I told, right? So the DC bus should be maintained at around 400 volt. So if we maintain voltage around 400 volt, then only we can exchange the power between source and load. Okay, and vice versa. Okay, that because battery can be act as a load as well as source. Okay, so we can exchange the power in both direction. Okay, so in order to maintain the DC bus voltage 400 volt. Okay, so here we are going to apply voltage control method for this bidirectional converter. So for that we are measuring the voltage here. Okay, DC link voltage that going to be compared with the 400 volt, and we are taking the error voltage, and that going to be processed via PA controller. That PA controller will be generate the duty cycle. So this is a duty cycle, and duty cycle going to be processed via PWM generator. So this PWM generator going to be generate the pulse for that bidirectional converter. So this pulse going to be given to, so we are taking this pulse and given to that bidirectional converter. So this voltage control method, right? So this voltage control method will be take care of that DC bus voltage maintenance around 400 volts. So it's going to be maintained around 400 volt. Okay, and also there is excess power in the PV, then it will going to be charged. There is no excess power, then it will going to be discharged according with the condition we made in the inside the simulation. Okay. So next to process, we go with the grid integration. Okay. So in order to integrate with the grid, right? So that in DC bus we are going to connect the inverter. So this is a inverter, or we can call it as converter. Okay, because it is going to be operate in both directions. Okay. So it can take the power from the DC bus to grid, and also can take the power from grid to DC bus. Okay, so it will be act as in both directions. So this is a bidirectional converter. Okay, bidirectional AC converter we can call this. Okay, bidirectional AC converter. So it will be operate in both directions. Okay, and next we have that filter. So LCL filter. Why we are using this LCL filter? Because the inverter output having square wave, right? Pendulum square wave. Okay, so that does not match with that grid voltage. We need to match with that grid voltage. Okay, so for that we need this filter. So this filter used to filter up that harmonic component in that inverter output voltage. Then it can be easily synchronized with the grid by means of PLL method. So in order to synchronize, right, so we need to filter out that harmonic component from that inverter output voltage. So then we can easily integrate with the grid and also synchronize with the grid. Okay. Now we need to make some control logic. Okay, not to control this inverter. So in this, how we are going to control here? We are going for current control method. So current control in the sense we are going to generate some reference current. So that reference current, based upon reference current, so this inverter going to be operate in the both direction. Okay. So how it going to be operate in both direction? I will explain now. So for that we need to measure the PV current. So here you see that. So we need to measure the PV current, and then we need to measure the SOC of the battery. Okay. So these are the two inputs for generating the I reference. Okay. So how we are going to generate the I reference? So just you click this one. Then here you see that, right, you will get that state flow. So here I am consider that two condition. Okay, two grid and from grid. Okay, two grid in the sense we are sending power to the grid. Okay, from the DC bus. Okay, that mean by means of PV source as well as by means of battery. Okay, so here we have to provide some current reference. Okay, so current reference I'm consider I reference equal to 2. That means we are sending 2 amps peak current to the grid. Okay, if suppose IPV is less than 0.5 amps and then SOC of the battery is less than 10 percentage. Okay, so in this condition battery is having less state of charge, so we need to charge the battery. Okay, so during this condition, and also there is no power in the PV. Okay, PV current is less than 0.5 amps. Okay, that is not having any enough power to charge the battery. Okay, so for that purpose we need some power, right? So that power going to be taken from the grid. Okay, during this condition, right, what happened, right? So we are making current reference equal to minus 10 amps peak. Okay, that means we are taking power from the grid. So this condition we are taking current from the grid to charge the battery as well as to supply the DC load. Okay, already we have some DC load, I will explain. So in order to supply the DC load as well as to charge the battery, we are taking the power from the grid. Okay, that for the condition for this IPV is 0.5 and the SOC is less than 10 percentage. Okay, if IPV is more than 0.5 amps and the SOC is more than 10 percentage, we are supplying power to the grid. Okay, so this is the logic we implemented for a inverter control of that grid. Okay, so now we are having that reference current. Okay, so here, so this is only magnitude, right? For not to control inverter, so we need to convert that reference current magnitude into sinusoidal form. So for that, here we are going to do that calculating the sine cosine waveform. So for that I am going to measure the grid voltage. So here I am going to measure the grid voltage. So the grid voltage is given to that PLL. and then the output of PLL nothing but omega t. So omega t going to be processed via sine and cosine, sine omega t and cosine omega t. So finally we are getting sine and cosine waveform from the PLL. So the use of PLL here is for synchronization of that inverter with respect to the grid. Okay, so for that purpose here we are using that PLL for generating the omega t phase angle with respect to time. After calculating the sine omega t and cos omega t, so next you have to take that reference, right? So here you see that, right? So we are taking that I reference and going to be multiplied with the sine omega t, and then this is single phase, right? So just we are omitting that cosine concept, so we are not using that cosine concept. So we are taking that AB reference. So that AB reference going to be convert into DQ form. Otherwise we are converting that AB into alpha beta. Okay, alpha beta quantity. So here we are converting AB to alpha beta quantity, and finally we are having alpha quantity and beta quantity. Okay, so next we are going to measure the current. Okay, so here we are measuring the current. So this is actual current of the inverter. Okay, output current of the inverter. Just we are going to measure that output current, and that is known as here A quantity, and then this is single phase. The remaining will be considered as 0. Okay, considered as 0, and then here we are going to convert that AB quantity into alpha beta. Okay, alpha beta quantity. So now we are getting the alpha and beta quantity actual, right? So here we have reference. Okay, so this reference is given here, and then the actual alpha beta is taken from here. Okay, next we have to implement current controller. So here we have current controller. So current controller going to be process uh, alpha actual and alpha reference, beta actual and beta reference. Okay, and it going to be processed via PA controller, and it will be generate the control signal. Okay, so control signal in the form of alpha and beta. Okay, next to process we are converting that alpha beta quantity into AB quantity. Okay, so here we are applying that alpha beta to ABC quantity, and then we are going to consider only quantity A because it's single phase. Okay, so next we are going to process, right, this A quantity, right, going to be processed via PWM generator. So this is sinusoidal PWM generator. When process that control signal via sinusoidal PWM generator, then it will be generate the 4 pulses. So here we are getting the 4 pulses for that inverter. Okay, so this 4 pulse going to be is to control this inverter. Okay, so what will be happen according with that reference current. Okay, so inverter going to be controlled in the either of the one direction, right? So that means it will be take the power from the DC bus, or it will be take the power from the grid. Okay, so this will happen in the control logic. Okay, so now I'm going to explain the results. Okay, so first initially I'm going to fix the state of charge now 50 percentage. Okay, now we are going to check the result of the system. So here we have to measure different kind of quantity. Okay, so here we are measuring the PV measurements, PV voltage, current and power, and we are measuring battery voltage, battery current, and DC bus voltage, DC load current, DC load power. So here we are consider DC load will be 1000 watts. Okay, and then here we are measuring SOC of the battery. Here we are measuring inverter voltage, that means grid voltage, inverter current and grid current. Okay, now I'm going to simulate this model. So now we are fixing that the SOC of the battery is 50 percentage. So when we are fixing that SOC of the battery is initial SOC will be 50 percentage. So what will be happen in the system we are going to explain now. I'm going to explain. Okay, and also I need to provide another thing. Here you see that, right? So here we are varying that irradiation. every 0.3 seconds, right? 0, 0.3 seconds, 0.6, 0.9 and 1.2. So here we are varying the irradiation 1500, then 10, and then again 500 and 1000. So we are varying the irradiation from 1000 to 500, 500 to 10, and then 10 to 500, and 500 to 1000. Okay, for every 0.3 second. Then you have to check the results. So here first I'm going to explain about PV. Okay, so the PV voltage, right, is maintained around to 245 volt, right? When that irradiation is 1000 watts per meter square. So when 1000 watts per meter square, the PV power extracting around 2000 watts, but it will take around 0.2 seconds. Okay, at the time of 0.3 seconds, irradiation change to 500, then it will be comes to around 1000 watts. After 0.6 seconds, the irradiation change to 10 watts per meter square, then it will be comes to 0. The time of 0.9 second, the irradiation change to 10 to 500, then it will be comes to 500, sorry, 1000 watts per 1000. The time of 500 watts per meter square. The time of 1.2 second, irradiation change to 500 to 1000 watts per meter square, then it again comes to 2000 watts. Okay, so this is a result of PV, and also here you can see the variation of voltage also. Then here you can see the variation of current. Current initially is around 8 amps, and here you will see 4 amps, and here the current will be 0. Here is 4 amps and here is 8 amps. Okay, now comes to battery, right? So I'm going to zoom this battery voltage. Okay, so you will see that so during charging, right, that means here you see that during charging the voltage is increasing, during discharging, right, so voltage will be decreasing. Okay, so that you can see here, right? So voltage is keep on decreasing because of battery going for discharging mode. When go for charging mode, battery voltage is increasing. Okay, so that you can see here, right, battery voltage increase and decrease and then again increase. So battery voltage increase during charging, battery voltage decrease during discharging. And also you can see the battery current is negative, in the sense battery going for charging mode. Okay, battery is positive, battery current is positive, in the sense so battery going for a discharging mode. So next comes to SOC of the battery. So here you see that battery in charging mode. So after that, in this point, battery in discharging mode. So then battery going for a charging mode. Okay, so this has happened because of PV irradiation change, right? So whenever the PV irradiation comes to around 500 or less than 500, then during that time when SOC having enough SOC, the SOC of the battery is more than 10 percentage run, then battery try to discharge, need to supply the load as well as supply the power to the grid. Okay, so now here you see that red DC bus voltage maintained around 400. Okay, so this is a DC load current is around 2.5 amps, and then DC load power is around 1000 watts. Okay, so next you comes to here this point. So in this point you can see that this is a inverter voltage or grid voltage. Okay, and then this is a inverter current. So in the inverter current you can see here it will be maintained around 2 amps peak. So you can see that 2 amps peak. Okay, and then this is a grid current. Okay, grid current also maintained around 2 amps peak. Okay, so just I'm going to zoom little bit, so we will see that some clear picture of that grid current also. Okay, so that means during this condition, right, battery SOS is more than 10 percentage, and then during PV during night condition like that, right, the night means the radiation goes to 0. During that time, right, battery taking care of that supplying power to the load, DC load as well as grid. Okay, whatever current here agreed for the supplying for grid, right, so it will be supplied from the battery during that night time. So this is a first condition. And one more thing here you can see, right, so this is a PV converter current. So this is a battery converter current and DC load current, and this is inverter input current. So this is sum of all current at the common point, DC bus point, right, is around 0. Okay, so see that this is only 10 into 10 power minus 13, 10 power of minus 13, so it's almost 0. Okay, so that mean you can see here that the power balance happened perfectly in this system. Okay, so now I'm move on to that here, right, I'm going to check here, I'm going to change the initial SOC is equal to 10 percentage, and then I'm going to simulate the model, and then you have to check the result. So what will be happen when PV, sorry, battery SOC, we are going to consider 10 percentage at the initial. Okay, so we need to check that result also. Okay, so you have to wait for some time for completion of the simulation. After that I'm going to explain the detail about so what will be the result during this condition. Okay, and also you can see the variation of that different parameters. Okay, so here initially the PV power is 2000, after 0.3 seconds, right, it irradiation change from 1000 to 500, then PV power comes to 1000 watts per meter square. Okay, so now you can see here, right, battery charging during the first condition. For second condition, battery going for discharging. During this condition, SOC more than 10 percentage. Now you see that, right, it comes to the SOC of the battery comes to less than 10 percentage. Okay, PV power comes to 0. Now we can see here, right, we are receiving power from the, once again, so you see that in that when grid voltage and inward current, right, both are in opposite direction. If both are in opposite direction, we are getting power from the grid. Okay, that means in this portion grid will be supplying the power. Okay, that means the condition already told, right, IPV is less than 0.5 amps, and then SOC of the battery is less than 10 percentage. During that condition, right, we are getting power from the grid. So this is a condition, the second condition as per our settings in the inverter control. Okay, here also you will see that variation of voltage. Okay, and then battery currents. Okay, so this is a variation of PV current, voltage and power, and variation of battery voltage and current. And then this is a variation of SOC of the battery, right? So charging, discharging, again is charging and again discharging, charging according to the condition we included in the system. Okay, so this is a variation of DC bus voltage, load current, DC load power, and this is the current of the DC bus, sum of current in the DC bus. Okay, so here also that we are having current almost 10 power minus 12 only, so it's almost 0. Power balance happen in the system. Okay, system controlled effectively. Okay, so this is a working of model grid connected solar PV system with the P&O MPPT. So thanks for watching our videos. Kindly subscribe our channel and also click bell icon for notification about upcoming videos. Thank you so much. Bye bye.